I'm Dr. J, and this is my guide to counting. Now, counting can seem like a very basic idea, right? We learn this in preschool or in kindergarten. You just identify an item, that's number one, move to the next item, 2, 3, 4, and that's the process, right? No big deal. Well, it turns out that when sets get really large, trying to enumerate the number of items in that set can become prohibitive. And so mathematicians have a field called combinatorics. And combinatorics is really a fancy word of saying counting. And we're going to introduce today 4 formulas for easing the process of counting when sets are very large. In order to do this, we're going to first consider a set that we're pulling items from. So that's going to be our initial set, and it's always going to have n items. So we're going to be thinking of the items that we're pulling as numbered from 1 up to n. And now from that set, we're pulling items into a new set. And that new set has k elements in the set. And we're going to be pulling elements from that first set, so we might have a set that's, say, the numbers 1, 2, 3. Or we might have another set that's the numbers 2, 2, 3. And now there's 2 main questions that we're going to ask ourselves about this new set that we're constructing. The first question is, does order matter in that set? That is the set 1, 2, 3 the same as the set 3, 2, 1 or not? If order matters, if order doesn't matter, we're going to call it a combination. And if order does matter, we're going to call it a permutation. And when we use the notation for permutation, we will use a parenthesis rather than a bracket to indicate that this set is an ordered set, as opposed to the curly braces where the set is unordered. The second question that we ask ourselves is, can the elements in the original set be reused? That is the set 2, 2, 2 okay? Or do all the elements in the new set have to be unique? We're going to say if they can be reused, that is with replacement. Some others use with repetition. The opposite of this is just without replacement or without repetition. The main focus of today's video is this slide right here. So this slide says we always start with a set of n elements. We always get a set with k elements in the end. And the question is whether order matters or not, and whether the items can be reused or not. And so if we focus for the moment on the middle 3 columns of this table that I will be showing here, the main question is, does order matter or not? If order does not matter, but we get to reuse items, then we will call it a combination with replacement. If order doesn't matter, but we cannot reuse items, then we will call that a combination. And typically the without replacement will be implicit. If order does matter, and we can replace items, that is, we can reuse items in our second set, then that will be called a permutation with replacement. If we cannot reuse items, then it's a permutation with replacement, assuming that order does matter. Alright, now if I focus our attention on the right column of this table, this right column gives us some formulas to how to calculate the size of any set that has to do with this particular order or replacement mattering or not mattering. These formulas use some notation that maybe you haven't seen before. Hopefully you've seen the factorial symbol before. So the n factorial for an integer n is just n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So it's just the product of all those terms. And just reminding you that 0 factorial is defined to be 1. And the second formula here is this parenthesis with a number on top and a number on bottom. That's called the choose formula, and it's read n choose k, and that n choose k is equal to n factorial divided by n minus k factorial times k factorial. Alright, so that's the formulas that we'll be using depending on whether order matters and whether we can reuse items or not. The remainder of this video is going to talk about the right column. So it's going to give you 4 examples, 1 for each of these combinations, and give you an example of how to use the formula for that particular example. So here's the first example. In Yahtzee, Yahtzee is a game played with 5 6-sided dice, and when you roll those 5 6-sided dice, you get a collection of dice and order doesn't matter at all. And so the question here is, how many unique Yahtzee rolls are there? So, first off, we have to answer a few questions. We have to answer how big is the initial set, how big is our final set, does order matter, and do we have replacement or not? So working through those questions, our initial set, each die can be a number 1 to 6, so our initial set has 6 elements. The final set that we have, there are 5 dice, so we will have 5 elements in our final set. Then the question is, does order matter? And I just explained it a second ago, but when you roll those dice, order doesn't matter, right? There's no way to keep track of the order of dice, and so order doesn't matter when you're making a Yahtzee roll. For instance, 1 1 1 1 2 is the same as 2 1 1 1 1. For replacement, can items be reused? Well, you can see the roll up top and the roll just a second ago. Both of those allow you to have repeats, so yes, in fact, repeats can happen. So if you're looking for the number of unique Yahtzee rolls, then it turns out that this is an example of a situation where order doesn't matter, and you do have replacement, and therefore it's a combination with replacement. We can look it up on the table and find out that the formula for combination with replacement is this funky looking formula here. We just go and figure out what the definition for a choose function is. We plug it in and we calculate, and it turns out that there are 252 unique Yahtzee rolls. So that was an example of combination with replacement. Our next example is looking at a lottery jackpot calculation. So here in some lotteries you have white balls, and those white balls can be numbered, say, from 1 to 66. And you're going to draw those 5 of those 66 balls, and when you do so, you're not going to replace the ball back into the bin to be redrawn. Alright, so to start off with, our initial set has n equal to 66 possibilities, because there are 66 different balls. We have a final set. We only have 5 balls, just like we had the 5 dice, and so k is equal to 5. We think about order mattering or not, right? Whenever you see a lot of results like this, you always see them put in order, right? And so that's just a rearrangement that's done after the fact, so it doesn't matter what order the balls are drawn, and so order here doesn't matter. And then finally, can elements be reused? Well, I explained before that as you pull the ball out, you don't put it back in the bin to be redrawn, so no, items cannot be reused. And so this is an example of a combination without replacement. And we figured out what n and k are, so we can look it up on the table and plug in the values. So this is just 66 choose 5. Plug in the formula and do the calculation, and it turns out that we have about 9 million unique lottery draws when there are 66 balls and you draw 5 of them. The next example is looking at passwords. Here's a very simple example, thinking about an 8-digit password. So suppose the requirement is that it's 8 digits and that you can only use lowercase English letters. So you think about the initial set. The initial set is the set of all English letters. There are 26 letters in the English alphabet, so n equals 26. Now, when we construct our password, it can only be 8 digits long, so the final set is 8. And does order matter? Well, yes, in a password, order matters, because Axtcumby is not the same as Yumbaksa. Now, lastly, does replication? Well, can we reuse any of the digits? We didn't explicitly state here, but generally in a password you are allowed to reuse digits, and therefore we're going to allow digits to be reused here. Alright, so because order matters and we can reuse digits, this is now a permutation with replacement. We figured out n, we figured out k, so we can plug it into the formula that we look up on the other table, that is n raised to the k, or 26 to the 8th power. And we can do the calculation. We can find out there are about, 209 billion passwords for this particular password policy. Our next example is a clinical trial example. In a crossover clinical trial, you have a number of patients, but each patient gets multiple treatments. So in this case, this particular patient got treatment D, then followed by treatment A, then followed by treatment C. And in general, patients don't get the same treatment twice. So they get unique treatments, but order matters because in a crossover trial, one of the things that might occur is that there might be a carryover effect. In this case, the treatment D might affect the results of the treatment A coming after it. And so in fact, yes, order does matter. In this example, if there's 4 treatments, our initial set has 4 possibilities, A, B, C, D, as they're labeled here. Our final set is 3 because each patient is going to get 3 different treatments. Does order matter? I was trying to explain a second ago. Yeah, order matters, right? And so order is distinct here because there are these carryover effects. Finally, can we reuse items? Sure, we can, no, we can't reuse items. I just said that typically in these trials, people only get 1 treatment. So we will only give each person, every treatment they receive will be different. So Order matters, but we can't reuse items. This is an example of a permutation or a permutation without replacement. We can look it up on the table and we can find that the formula is, in this case, 4 factorial divided by n4 minus 3 factorial. And that calculation says that there are 24 different possible treatment plans for this particular example crossover clinical trial. Alright, so the main purpose of today was to get an example of using each of these different counting methods and how we can use the formulas to calculate the size of the sets that are constructed depending on whether order matters and whether there is replacement, that is, items can be reused. In the next slide, really the next 4 videos, we'll be going over each of these counting methods in a little bit more detail, and in particular we're going to try to show how those formulas arise. So where do those formulas come from, and provide some intuition behind that so that you can perhaps create your own formulas for your own particular situation that don't fall neatly into one of these 4 categories. Until next time, have a great one.